So let's start with binomial theorem in this class. So we'll have to first understand something called Pascal's triangle, which will help you in finding the coefficients in a binomial expansion. So we have a triangle called Pascal's triangle, and we'll try to relate it with the binomial expansion. So we'll write 1. Then below that, in the next row, we'll write 1 on either side of it. In the next row, we'll again write 1 on either side of this. And then we'll add these two and write the result here. Like this forms a triangle. Sum of any two is equal to the third one. Again, write 1 on either side. Adding these two values will give you this number. And adding these values will give you this number. So the next row is 1331. The next row is 1331. Again, we have 1 on either side. Adding these two will be 4. Adding these two will give you 6. Adding these two will give you 4. Again 1. So like this, you can write down several rows in the Pascal's triangle. So one more row I'll write, 1 on either side. Add these two, you are going to get 5. Add these two, you will be getting 10. Add these two, you will be getting 10. Add these two, you will be getting 5. Then again, this is 1. So one thing that you can observe is if you look at the terms equidistant from either side, they have equal coefficients. Like the second value from beginning and the second value from ending are same. Third value from beginning here is 10. Third value from ending is also 10. So the numbers equidistant from either side are same in this Pascal's triangle. And any two vertices you add, you get the third vertex. This is called Pascal's triangle. Then how is it related to binomial theorem? So in the expansion of x plus a power 0, you'll be just getting the answer as 1. So that 1 is nothing but this value. In the expansion of x plus a power 1, you'll just get x plus a only. That is, you have 1x and 1a. This 1 and 1 are nothing but these coefficients which I've written here. So when the power is 1, the coefficients in that expansion will be nothing but the terms in this row, the numbers in this row. So for n equal to 0, this is for n equal to 1, the coefficients in the expansion are 1 and 1. And these coefficients will occur in the expansion of x plus a whole square. X plus a whole square will have x square plus 2 into x into a plus a square. So the coefficients in this expansion are 1 to 1, which you can see here. So for power 2, there will be 3 coefficients, which are nothing but the numbers in this row. Similarly, for power 3, you'll get this. For power 4, you'll be getting this. And for power 5, you are going to get this. So if the power is 5, there will be 6 coefficients. If the power is 4, there will be 4 coefficients. So seeing this pattern, if you want to write x plus a power 3 or something, what will be the coefficients when the power is 3? There will be 4 coefficients. That is 1331. 1331. And suppose if the power is 4, how many coefficients will be there? 5 coefficients, and there will be the next row. That 14641 will be the coefficients. 14641 are coefficients. And in case if the power is 5, there will be 6 coefficients. And what are they? 1, 5, 10, 10, 5, 1. These are the coefficients. Now, how do you write the terms of the expansion? So whatever is the first value, first variable, write that with index as 3. As you proceed toward the right, the power will decrease. Then x square, x power 1, x power 0. The power will decrease by 1 unit. And the power of a will start with 0, increase up to the index. A power 1, a power 2, a power 3. That's how you write the terms and just put plus signs. This is the expansion for x plus a cube. Similarly, if it is x plus a power 4, the power of x will start with 4. And it keeps on decreasing. Then x cube, x square, x power 1, x power 0. Whereas the power of a will start with 0, increase up to the index. A power 0, a power 1, a power 2, a power 3, a power 4. All plus signs in between you can write. So the last one I'll just erase and write properly. That was 1 x power 0, a power 4. And this one again, you'll start with x power 5, x power 4, x power 3, x power 2, x power 1, x power 0. And the power of a will start with 0 and it increases by 1 unit. Then a square, then a cube, a power 4, and a power 5. So clearly we can see that all these coefficients can be written with Pascal's triangle and we can easily write the expansion. But to what extent are we going to use Pascal's triangle? So in this slide, I could fill only up to this number, this row. Probably if I take a bigger chart or something, I may fill another 5 or 10 more lines. But if the power is something like 100, you have to write pages to write this with Pascal's triangle. That is why we write a generalized theorem called a binomial theorem. Okay. But before we proceed, we can just see that the index of the binomial expansion, if it is n, number of terms will be n plus 1 whenever it is a non-negative integer. So always you observe that in a binomial expansion, number of terms is equal to the index plus 1. And when will this hold? Not always, because when the power is negative integer, you'll have infinite number of terms. For fractional power also, you'll have infinite number of terms. So when the index is non-negative integer, then only this is valid. Non-negative integer, this is valid. Otherwise, this is not valid. So that we'll discuss later for infinite number of terms. But for the case where n is a non-negative integer, the number of terms in the expansion is index plus 1. This is the first observation that you can do. In every term, what is the sum of powers of x and a? In every term, the sum of the powers of x and a, the sum of powers of x and a is equal to index. X and a is equal to the index. Is equal to the index. And the power of x will start with index, decrease up to 0 as we move from left to right. So we can say as we move from left to right, as we move from left to right, the power of x starts with index and decreases up to 0. And decreases up to 0. So it starts with the index. For the last term, it goes to 0. And as we move from left to right, the power of a, as we move from left to right, the power of a starts with 0. The power of a starts with 0 and increases up to index. And increases up to index. So these are the observations that you can see in a binomial expansion whenever the power is a non-negative integer. So now, as the power becomes larger, the Pascal's triangle is not feasible for us. So we are going to use a generalized theorem called binomial theorem. So we call it as binomial theorem for non-negative integral index. Non-negative integral index. Binomial theorem for non-negative integral index. So if you consider the binomial expansion for x plus a whole power n, if you have to write in general, so the coefficients which you wrote earlier with Pascal's triangle can be written with the formula NC0 is the first coefficient, NC1 is second coefficient, NC2 is the third coefficient, then NC3, and so on up to NCn is the last coefficient. The power of x will start with n. As you proceed, it decreases by 1 unit, x power n minus 2, x power n minus 3. And at the end, it becomes power 0. The power of a will start with 0. There will be plus sign everywhere. A power 1, a power it increases and goes till a power n. So that is how you can write down the binomial expansion. This is called binomial theorem for non-negative integral index. And to find these coefficients, we have a formula. The formula is NCR is equal to factorial n divided by factorial r into factorial of n minus r. Using this formula, we can calculate all coefficients. But every time, instead of applying the formula, you can just remember for NC0 and NCn, the value will always be 1. NC1 will be n and NCn will also be n. NCn is 1, sorry. NC1 is n.
NCn minus 1.
This is same as NCn minus 1 because we have a property that NCR is same as NCn minus r. So NC0 is same as NCn minus 0, which is n. NC1 is same as NCn minus 1. NC2, the method of writing this is start with n. If there is 2, write 2 numbers backward, write 1 into 2. So every time instead of using factorial, you can use this. If it is NC3, start with n, write 3 numbers backward. Start with 1, write up to 3. So that means if it is NC4, you'll start with n, write 4 numbers backward, n minus 1, n minus 2, n minus 3. And in the denominator, we'll start with 1, right up to 4. This is a shortcut method to calculate instead of always applying the formula. So that is how you can find binomial coefficients and you'll be able to write binomial theorem for any higher power. This is x plus a power n. So you now observe that the pattern you can see, the first term is NC0, x power n minus 0, a power 0. The sum of the powers of x and a is equal to the index. Second term, it will be nc1 x power n minus 1 a power 1. Third term is nc2 x power n minus 2 a power 2. Observing this pattern, we write something called tr plus 1, which is called general term of the binomial expansion. So that is whenever they don't ask for full expansion, instead you want to find only 2 or 3 terms or only one term, we can use the formula instead of expanding it fully. So for third term, you got 2. For second term, you got 1. So r plus 1th term, you'll get NCR. The power of x will be difference of these two, upper and lower subscript. So n minus r. The power of a will be equal to the lower subscript r. So this is called general term of the binomial expansion, NCR x power n minus r a power r. So always r plus 1th term is the general term of the binomial expansion. This is said to be the general term in a binomial expansion. And instead of writing all the terms, because all the terms are going to follow this pattern, like for r equal to 0 here, it is the first term. For r equal to, it is the second term and all. So instead of writing such a big expansion, we can write in short form. So the expansion in short form can be written as sigma of general term, sigma of NCR x power n minus r, a power r, where r equal to 0 to n. So whenever you want to write short form notation, we can always write like this. And in particular, suppose if a becomes 1, it is x plus 1 whole power n equal to sigma r equal to 0 to n, NCR x power n minus r, if a is 1. And suppose if it is a plus x power n, how do you write that? Sigma r equal to 0 to n. The order of a and x got interchanged. So NCR, first you will have to write a power n minus r, then x power r. The order of x and a got changed, the powers will change. And if it is 1 plus x whole power n, you replace a with 1, you will get sigma r equal to 0 to n, NCR x power r. So all these things are standard expansions. You can remember the short forms. Similarly, if there is a negative sign in between, so in the general term of the expansion, when you write NCR x power n minus r, you'll have minus a power r and r equal to 0 to n. So that minus sign can be separated out and you can write sigma r equal to 0 to n, NCR x power n minus r a power r into minus 1 power r. You can actually write in the beginning like this. Whenever you have r as odd number, it will be negative. R as even number, it will be positive. So when you open this expansion, basically it will have NC naught x power n minus 0 a power 0 minus NC1 x power n minus 1 a power 1, alternately plus and minus, starting with plus sign. For even coefficients, you'll have plus. For odd coefficients, you'll have minus. NC2 x power n minus 2 a square minus NC3 x power n minus 3 a cube and so on. This is how you write down the expansion. Last term, if you want to write, just you have to write minus 1 power n, NCN x power n minus n, a power n. This is how you write down the expansion in the expanded form, but this is a shortcut notation. So this is short form notation and this is expanded notation. And whether there is plus or minus, the number of terms is n plus 1 only. It depends on the index. So here also number of terms is n plus 1. And now, if I combine the expansions, what would I get if I add these expansions and subtract the expansions? So when I add them, what kind of terms are going to cancel out? The alternate terms with NC1, NC3, which have minus signs, will cancel out. NC0, NC2 will occur double time. So when you add the expansions, you'll get 2 times NC0 x power n minus 0 a power 0 plus NC2 x power n minus 2 a square plus NC4 x power n minus 4 a power 4 and so on. This kind of terms you are going to get. And if you subtract, you will get the odd terms. 2 times NC1 x power n minus 1 a power 1 plus NC3 x power n minus 3 a power 3 minus, plus NC5 x power n minus 5 a power 5 and so on. This is the result obtained by subtraction. So even though there is 2 times, if you have NC not 2 times, you don't count this as 2 terms, you count as only 1 term while counting the number of terms. So NC not term is twice, NC2 is twice, but if it is a similar term, you don't count separately, you will count it as 1 unit only. So based on this now, suppose if I ask you in the expansion of x plus a power 100 plus x minus a power 100, what are the number of terms?
50.
Number of terms would be 50 or 51?
51.
51, because you need not write the full expansion, but what kind of terms will be there? NC naught means When you add, you'll have 100 C0, 100 C2, this kind of terms. 100 C4 up to 100 C100. So 2 to 100, if you say 250s are 100, so from here to here 50, but 100 C0 is there, so 51 terms. So number of terms, if they ask, it is 51 terms. If there is a plus sign. What if there is a minus sign? Then what is the number of terms? So what kind of terms will be there? 100 C1 would be there, 100 C3 would be there, up to 100 C99. So how many are there? 1, 3, 5 up to 99. From 1 to 100, you have 50 odd and 50 even. All odd numbers you listed out. So obviously 50 terms. The answer is 50. What about the case where the power is an odd number like 101 with addition and with subtraction? If the power is an odd number, what is the number of terms in these two cases? So in addition, you'll have terms like 101 C0, 101 C2, even terms would be there. So 101 C100. So again, 0 to 100 means again 51 only. And here you'll have 101 C1 odd terms, 101 C3. But earlier it was ending at 99. Here you'll have 101 also. So in this case, the answer will be again 51 because 101 C, 101 is also there. This answer is same for both. In even power, it is different. In odd power, it is different. So this is for number of terms in standard expansion. Now, suppose you consider number of distinct terms in the expansion of, for example, I give you 2x plus 3y plus 4z power 20. How do you find this? So what would be the number of terms in this expansion? So whenever you have x1 plus x2 plus x3 up to xr, you may have a coefficient before that, doesn't matter, power n. And if you want, you can have some a1, x1, a2, x2, where the a1, a2, a3 are all numbers, ar, xr, power n. If you have to find number of distinct terms for this type of problems with different variables, directly we can write the formula n plus r minus 1 c r minus 1. So where r is the number of variables, n is the index. So in this case, take n as 20. R as the number of variables, x, y, there are 3 variables, so 3. So if you apply this formula, n plus r minus 1 would be 22. C r minus 1 would be 2. And what is 22 C2? Start with 22, write 2 numbers backward and 1 into 2. So that will give you 11 into 21 and that is 231. This is the formula you can directly write. And if you have to write down the general way of that expansion, like for example, 2x plus 3y plus 4z power 20. Just like you wrote a binomial expansion, if I want to write the expansion, you just have to write sigma of some general term. The method to write general term is whatever is the index, you write factorial of that divided by, there are 3 variables. So take 3 variables k1, k factorial, k2 factorial, k3 factorial. 3 symbols like this. The first one should be raised to power k1. The second one should be raised to the power k2. And the third one should be raised to the power k3. And k1 plus k2 plus k3 should always be equal to the index. So the number of triplets which will satisfy this will give you number of terms. So whatever triplet satisfies, for example, if I write 1, 1, 18, that is one triplet. Or I can write 1, 2, 17, that is another triplet. Like that, you'll have many triplets. So for that, we have written a generalized formula. So how many such triplets are there means we could have used this formula by putting r as 3. So this is how you can write down general term, and sigma of general term is full expansion. So if they ask general term, don't put sigma. But if they ask you full expansion, put sigma of general term. And all the terms can be written by putting different k1, k2, k3 values. Of course, if there are 231 terms, they won't ask you to list out. But in particular, if you want a term, you can find it using this. Like I'll explain with a simple value. Like for example, all of you are familiar with the square formula. What is the formula for square? X square plus y square plus z square plus 2xy plus 2yz plus 2zx. This is the expansion. But you don't know if I give you power 5, power 10 and all, we don't know how to write. So what we are going to do, we'll observe a pattern here. So one, there's a term with power of x as 2. There is no y and z. So I can say y power 0, z power 0 for first one. And before this I have 1. So what I can do, the power is 2 here, right? Factorial 2. Divided by, write down the factorial of these powers. Factorial 2, factorial 0, factorial 0. Whatever powers of x, y, z are there, write that. When you cancel this, anyway, it is 1 only. Here, this is 1x square and that is matching. For y square, if you see, you write x power 0, y power 2, z power 0. Again, write the index 2 factorial by factorial of these powers. This, when you cancel, again, it is 1 y square. Like that, the next term, z square, you can write x power 0, y power 0, z square. The index factorial by factorial of 0, factorial of 0, factorial of 2. Then 2xy term, I can write x power 1, y power 1, z power 0. The 2 can be written as factorial 2 by, what is this factorial 2? Factorial of the index of the expansion by denominator will write factorial of the powers of x, y and z. 1 factorial, 0 factorial. This will simplify to 2, which is nothing but this coefficient 2xy. Like that, in the next term, you can again write y power, x power 0, y power 1, z power 1, this term. And you can write index factorial by factorial of these powers. And 2zx term also, you can write factorial 2 here, and x power 1, y power 0, z power 1. In the denominator, you can write factorial 1, factorial 0, factorial 1. So in all the terms, what you can observe, the sum of the powers of x, y, z is equal to the index. And in the coefficient for every term, what did you write? The factorial of the index divided by factorial of the powers of x, y, z. So instead of writing this addition, you can just write that in short form. What is the short form? You can just put a sigma and write x, y, z will have some powers. Suppose you assume that the powers of x, y, z are k1, k2, k3. So in the first case, k1 is 2, k2 is 0, k3 is 0. In the second case, k1, k2, k3 means 0, 2, 0. That is another triplet. So what is there before the power index factorial? So 2 factorial by factorial of k1, k2, k3. And in every term, what is k1 plus k2 plus k3? The sum of the powers is always equal to the index. With the same logic, I wrote for the general case. So whenever there is some expansion like this, you can just write index factorial by, there are 3 variables. So write k1 factorial, k2 factorial, k3 factorial, and you'll raise this with k1, this with k2, this with k3 and write it. The sum of the powers k1, k2, k3 should always be 20. These 3 variables should always add to 20. And any triplet which will satisfy this will give you a term. So the number of terms here, you see this example. Number of terms here is nothing but number of triplets. 2, 0, 0 is one triplet satisfying this. 0, 2, 0 is another triplet satisfying this. All those triplets together will be number of solutions. So number of triplets or number of solutions is nothing but number of terms. With the same logic I'm saying. So if you find out the number of solutions of this equation, it is equal to number of terms in this expansion. And for writing the number of integral solutions, we have a formula in permutation that we have used here. This we learn in permutation chapter. We'll do it later again for the proof. But right now, you can just remember the formula. When I do permutation or at the end, I have to do rational index. We have to combine that with the permutation and do this. So for the time being, just remember the formula. I'll show you the derivation later. I hope it is clear now.
Yes, sir.
Okay. So if I give you something like a plus 2b plus 3c plus 4d power say 12. If I ask you number of terms, what should you write? Terms, number of terms means distinct only anyway. So we have to write n plus r minus 1c, r minus 1. What is n here? The power. And what is r here? Number of variables. A, B, C, D, 4 variables are there. So 4. So 12 plus 4 minus 1, c 4 minus 1. 12 plus 4 is 16 minus 1, 15, c 3. What is 15c3? Same as 15 into 14 into 13 by 1 into 2 into 3. So 2 you can cancel 7 times, 3 you can cancel 5 times. So 5 into, yeah, 455. So you can write down number of terms like this, distinct terms. Okay, I hope all of you are clear with it. Now let's say, for example, I have an expansion like 1 plus x square power 10. How many terms will be there in this? Here, you don't have different variables, you have same variable, then this formula will not be valid. Whatever I gave now is not valid here. So previous formula is not valid here. So then how to write number of terms? What will be the highest power? This is 2, this is 10, 2 into 10, 20. So you can say this expansion will usually contain x power 0 with some coefficient. It's not a binomial expansion, so we should not write NC naught because it is trinomial. 3 terms are the trinomial expansion. You can just say some A naught. Then A naught we have to find. Later we'll know how to find that. But what is the general format for finding number of terms? We'll see. So then there will be some A1 with power 1, A2 with some power 2. Proceeding like this, the last term would have power of x as 20 and it will be A20. So the powers are varying from 0 to 20 means number of terms is therefore 21. So number of terms is equal to 21. In general, you can say if there is something like 1 plus x square power n, what is the formula for number of terms? It will be 2n plus 1. So if you have to write number of terms, this is the formula. And even if you have something like x plus 1 plus 1 by x power n, even here you can take LCM. It will be something like this divided by x power n. The number of terms will not be affected. And if the power of x changes in the expansion, like it is x cube plus 1 by x cube power n, even then number of terms will not be affected. It is still 2n plus 1. So if it is x power m plus 1 by x power m whole power n, where m is some power, but number of terms will be still 2n plus 1 only. So when I say number of terms, I'm talking about distinct terms only. So the multinomial formula will not be valid for number of terms. Why? Because some terms with similar powers are clubbed together and it will reduce the number of terms. That is why that formula is not valid. When there are 3 different variables, it is valid. But if you have same variable repeated, it is not valid. So is this clear?
Yes, sir. Sir, it can be till x cube also, right? Or only till 3 terms?
No, you can
Okay,
have
sir.
more number of terms. Like you mean to say instead of 3, one more inside.
Yes, sir. Like 1 plus x
Then it
square.
won't work. Only for this type it will work. This whatever format I wrote, it's going to work only for that. So this is about number of terms. Now I'll give you a question. The number of terms in the expansion of a plus b plus c power 50 plus a plus b minus c power 50 is. So whenever I said number of terms, I mean to say distinct terms only. I'm not particularly writing, but distinct terms. So try and tell me the answer for this. So without using any formula, let us go with binomial. For example, if I consider a plus b as some x, so then it is something like x plus c power 50 plus x minus c power 50. I'll name that expression as some e. So it's a binomial expansion with plus sign. Whenever you add what kind of terms, you'll get 2 times 50 c naught x power 0, 50 minus, or x power 50 minus 0, which is 50 c power 0. Then you'll get 50 c2 x power 50 minus 2 c power 2. So you'll get this kind of term 50 c4 x power 50 minus 4 c power 4. Like this, what will be the last term? 50 c50 x power 0 c power 50. So you'll get this kind of terms. Now, what is x power 50 actually? X is a plus b. So this is a plus b power 50, which will have how many terms? 51 terms. So I'm writing number of terms equal to. So in this only there are 51 terms. Like x power 50 itself is a plus b power 50, which is a binomial. 51 terms into c power 0 will still not change the number of terms. Plus, then x power 48 will have how many terms? It's a plus b power 48 will have 49 terms. Into c square will not change the number of terms. X power 46 is a plus b power 46, which will give 47 terms. Like this, the last one, x power 0 will be 1. So all odd numbers from 1 to 51. You write in reverse order. It will be, yeah, so we were doing this in the previous lecture. It got disconnected. So for finding the number of terms in this kind of expansions, which is sum of two trinomial expansions, since there is a similarity between these two, you can put a plus b as some x. It would represent x plus c power 50 plus x minus c power 50. Now it is looking like adding two binomial expansions. And whenever you're adding two binomial expansions like this, one with minus and one with plus, the odd terms will cancel out, even terms will remain. So C naught term, C2 and all are remaining. And at the end, you'll have 50C 50 because the power is 50. So if you look at the number of terms, this x power 50 is actually a plus b power 50. So that will have 51 terms. And x power 48 is a plus b power 48. That will have 49 terms. Proceeding like this, you will get all odd numbers 51 plus 49 up to 1 backward. So you write this in the reverse order 1 plus 3 up to 51. And since this is an arithmetic progression with 51 terms, the sum can be written as number of terms between first term plus last term. So this is 51 into 52 by 2. So the answer is 51 into 26. So like this, you can convert into binomial and find it.